A multi-optima genetic algorithm is a specialized form of genetic algorithms that attempt to solve problems that have multiple correct answers. Typically, this includes problems with multiple global optima, but it could include a problem with a single global optimum and one or more local optima. They're also often called niche genetic algorithms. So there is an issue with genetic algorithms, and that is that there's a category of problems that genetic algorithms are not very good at solving. These types of problems have been given different names, from multi-optima, multimodal. For minimization problems, multi-basin has been used. But these types of problems require a specialized form of genetic algorithms to solve. So this video assumes you know what a genetic algorithm is. If not, you might want to check out some other videos on YouTube describing what they are. But here's kind of a brief overview. A genetic algorithm is a computer programming algorithm that searches large domain spaces for optimal values. And the algorithm basically begins with an initialization phase where it randomly selects some number of possible answers called the population, and then it loops through sometimes hundreds or thousands of times through three functions. The first one is selection, where it selects pairs of possible answers based on how well they solve the problem, which is called fitness. Then there is crossover, where it creates new possible answers from segments of each possible answer from the selection phase. And finally, there's mutation, where it alters some of the possible answers to explore new areas of the domain. So if we look at an example like this, the first generation of a genetic algorithm is purely random possible answers. So here we have this very unusual looking function, and we want to find what x value produces the greatest y value. So it's somewhere around here. Our little red dots are possible answers. That represents the first generation. And you notice that they're kind of all over the place. Once we run through the three operations, we go to generation number 2. We notice that the answers are starting to come closer together. They're getting better or closer to the optimal value. We run this hundreds, maybe thousands of times. When we get to generation 1000, we have all the individuals clustered around or converged around some optimal value of x. And that's how a genetic algorithm works. What do you think a genetic algorithm would do when it was faced with a problem like this function? This is a segment of the sine function. And how do you think a genetic algorithm would work against a function like this? Well, if you try it and run it multiple times, you'll notice that sometimes a genetic algorithm will find this optimum. Sometimes it will find this optimum on the right, but it doesn't find both. And if you have a problem where you want to find both, then a genetic algorithm is not a very good choice, at least the standard algorithm. Here's another example. This also is another section of the sine function. And how do you think a genetic algorithm would solve this? Well, it more than often would find the optimum on the left because it's greater, but sometimes would find the optimum on the right, but would not find both. And that is the problem that's faced with traditional genetic algorithms. So the term multi-optimum genetic algorithm or niche genetic algorithm is a classification of genetic algorithms where they took the basic genetic algorithm functions and modified them or enhanced them in some way to solve these types of problems. This algorithm is often referred to as the shared fitness algorithm, or Goldberg and Richardson's 1987 algorithm from a paper they published in 1987. It's one of many examples of multi-optima genetic algorithms, but there are many out there. And how this works is, instead of using the fitness in the selection process for an individual, it uses a new function called shared fitness. And shared fitness can be defined as the fitness of an individual divided by m sub I. And if we think of the individual we're evaluating as x sub I, then m sub I is this equation here. You basically take the individual you want to find the shared fitness for, which is x sub I, and you compute you evaluate its distance to every other individual in the population. That's why the sum is here from J1 to N. And you take that distance and you put it into this function SH. And SH is defined here. And if you run a few values through it, you will realize that what happens is if an individual is close to other individuals in the generation, then its fitness, its shared fitness, is decreased in relationship to other individuals in the population. And if an individual is kind of alone, there's not other individuals around it, its shared fitness will be relatively increased compared to the other individuals in the population. So what this does is it preserves these individuals that are in what we would call empty areas of the domain and allows them to investigate those areas, because with a higher shared fitness, they're more likely to be selected in the selection process. And it gives the genetic algorithm more time to investigate these other areas of the domain for possible local or global optimum. And if you want to learn more about it, you can find the paper and download it, and you can code it if you want to. Here are some of many papers that were written on the subject of multi-optima genetic algorithms. They started back in the 1970s and go all the way up to modern day. This one in the second column, second down, Brown MS 2010, is my dissertation, a species-conserving genetic algorithm for multimodal optimization. And you can download that and read it for free. And most of these papers, if you check at scholar.google.com, most of them you can find for free as well.